Okay, so today we have Marina Moleti, who will tell us about Calabi-Yau threefold flops as quiver varieties from monopole deformations. Take it away.
Okay, so first of all, hi everybody. Thank you to be here. So today I will present a research project, the current research project of my PhD, which I did in collaboration with Roberto Balandro, my supervisor, who is based at University of Trieste, and Professor Andres Collinucci from Université Libre de Bruxelles. Let me just start by okay. Sorry. Let me just start by giving the background and the motivation behind my research activity. So what basically interested in is in establishing and exploring correspondences between the dynamics of quantum field theories in general, in particular with some degree of supersymmetry, and geometric structures. And I want to use these correspondences in order to tackle like problems that are not approachable with the usual techniques, both in quantum field theories and in pure geometric in the purely geometric realm, so in the realm of algebraic geometry. And the perfect framework to study these correspondences, so a perfect framework is represented by string theory, as testified by many examples like Calabi-Yau compactifications, brane modeling, geometric engineering, and so on. So for this present project, what I'm focusing on is the characterization of the low energy dynamics of deep branes, which can be used as probes, which can be interpreted as probes of the transverse space geometry. So what I want to show is that there is a relationship, a direct relationship between the structure and the components of the quantum field theories that describe the low energy dynamics of the brane and the geometry of the space-time, which is transverse to the brane world volume. So in particular, I will focus on the characterization of the moduli space of these theories and give an explanation of how they reflect the probe geometry. So in some very trivial cases, it even happens that the moduli space is isomorphic to the probe geometry. So as for the example of a D3 brane that probes a complex, that probes purely flat space, C3. In this case, the D3 brane preserves half of the supersymmetries of the underlying string theory, so 16 supercharges, and the resulting low energy effective field theory is represented by U1 vector multiplet. And notably, this U1 vector multiplet contains three complex scalars. So the moduli space of this theory is trivially represented by the expectation values of these scalars, which indeed form a space which is isomorphic to C3. And indeed, they represent their interpretation of these webs is the following. So these webs represent the position of the D3 brane along the three complex directions that generate the C3. So now I want to move to more interesting cases. Because as we know, the dynamics of branes the low energy description of brane dynamics becomes more and more structured and exotic. The more intricate is the geometry which is being probed. So and paradigmatic the most interesting examples are the cases in which branes probe singular geometries. So a paradigmatic example of these cases is represented by DT branes on AD orbifold singularities, which gave rise to the well-known quiver gauge theories. So let me just briefly mention what an ideal orbifold singularity is. So this can be represented as a complex surface X2G, which is constructed as an orbifold, as a C2 modded by a discrete subgroup of SU2. And via correspondence, which is known as McKay correspondence, each of these subgroups, distinct subgroups of SU2, is associated to the structure of an algebra of a Lie algebra of type A, D, or E. So an example is represented by AN, which is by an AN singularity, which is associated, which is represented by an orbifold of type C2 over Z modulo n plus 1. And again, through this correspondence, the structure of the Lie algebra of AN, which is synthesized by its linking diagram, also encodes the structure of the geometric structure of the singularity, and in particular the configuration of the exceptional two cycles that constitute the resolve, that characterize the resolved version of the orbifold singularity. So what is relevant to us is that at the singularity, new brane states with respect to the pure D3 brane states are defined, and these are called fractional D-branes. So we can think of the situation as a situation in which the pure D3 brane state decomposes at the singularity into n+1 fractional brane states, and each of these fractional states, fractional branes, is in one-to-one correspondence with branes, with D5 branes that wrap the holomorphic two cycles of the resolved geometry. So they are the limit, they represent in a sense the limit in which the size of these cycles goes to 0. So from the point of view of the dynamics of this system of branes, the low energy description corresponds to an effective field theory, which has half of the superstarness of the previous case. So we have an n equal to 2 four-dimensional gauge theory. And here the field content and the interaction of the theory are encoded in a Quiver diagram, which has the same shape as the linking diagram that is associated to the singularity. And here you see that each node is to be interpreted as an n equal to 2 vector multiplet, whereas the lines, so the double arrows connecting the nodes, represent bifundamental hypermultiplets, so charged only under the nodes that they connect. So what I want to show you is very briefly the correspondence in this case between the moduli space of the D3 brane on such singularities and the transverse geometry. So the transverse space to the D3 brane is represented by a Calabi-Yau threefold that is essentially a trivial fibration of an AD singularity over a transverse plane that we parameterize with a coordinate W. And here I have depicted the configuration, like the geometry schematically, and I've represented the complex plane as a line. And you can see that, you can interpret these cones, so these bidimensional cones, as copies of the AD singularity, with the tip of the cone that represents the singular point. And here I have drawn with different colors, so as red dots and blue dots, the states that represent respectively the fractional D3 branes, which can only sit which can only move along the singular locus of this geometry, and the pure D3 state, which instead can move freely along the non-singular part of the transverse space. So what is the moduli space of the theory? So this is an n equal to 2 supersymmetric theory. So the moduli space is a direct product of two branches. One is the so-called X branch, which is perturbatively defined as the space parametrized by webs of hypermultiplet scalars, and it's a hyperkähler manifold, so it can be constructed with the usual Nakajima-Cronheimer quotient construction. Instead, the Coulomb branch and the X branch is classically exact. The Coulomb branch instead is parametrized, at weak coupling by the webs of vector multiplet scalars. And classically, it's basically consists in the case of the AN singularity in C to the power to the power n+1, because in this case we have n+1 U1s, of which one is decoupled but still contributes to the Coulomb branch. So what I wanted to stress is that these two branches have very clear interpretation in terms of motion of the pure D3 state of the D3 state along the transverse geometry. In particular, the Higgs branch coordinates represent basically reproduce the AD singularity and describe the motion of the pure D3 brane state along it. Instead, Coulomb branch directions, which in this specific case are represented by the webs of the Coulomb branch scalars associated to all these n+1 nodes, parameterize the motion of each fractional brane along the complex plane, parameterized by W, which is the only portion of the space in which they can move, since it's the singular locus. So now I want to move. I want to move to a next example, which is a sort of can be thought of as a complication of the previous case, and in particular as a non-trivial fibration of an AD singularity, which basically gives rise to a threefold that now preserves half of the supersymmetry of the previous case. So we will have so we expect to have a quiver description that is that corresponds to n equal 1 for the theory for the case of a D3 brane. So, and well-known example of this non-trivial fibration of ADs is represented by the conifold geometry, which as an algebraic variety can be described, is defined as an equation, an homogeneous equation in C4. And here I have written with I've used different colors for the coordinates X, Y, and Z, and W in order to stress the interpretation of this geometry as a fibration of an A1 singularity, because you see that an A1 singularity, which is C2 mod Z2, can be described precisely as an equation in C3 of this form. So for any fixed value of W different from 0, this equation, the equation that specifies X3, is a deformed A1 singularity, so a completely desingularized A1. Instead, W equals 0 is the only point on the base of this vibration where the A1 singularity is completely recovered. So here I depicted the situation in order to stress the difference with the previous case. So with respect to the previous case, now you can see that the singular, so we just have only one singular fiber on the base C plane, and all the other points correspond to F fibers that are completely desingularized. So as a consequence, from the point of view of the fractional D3 brane states, since the fractional states are defined only at the singular point, you can see that they will never, they cannot have moduli of their own, so they cannot contribute to the moduli space in this case, because they are localized at the only singular point available. So all the moduli will describe the motion of the pure D3 state inside this total space, the total space of this vibration. And the structure of the low energy of QFT that develops on this D3 brane system is encoded in a quiver which is shaped precisely as an A1 quiver. But with the difference, with the crucial difference that this is an n=1 supersymmetric theory, and the superpotential, so that we had, even if I did not write it in the n=2 case, is now vanishing. So even if it's just for this for the abelian version of this theory. So when we consider a number n of D3 branes, superpotential will be non-vanishing. But what is important is that basically this quiver with the vanishing superpotential has a moduli space that reproduces the singular conifold geometry, and the algebra, so the quiver algebra associated to this quiver and to this specific quiver representation gives yields the resolution, so encodes the information about the resolved geometry. So so far, starting from the early 2000s, there has been like a great improvement in the characterization of the theories living on D3 branes at singularities, at Calabi-Yau singularities, but only specifically for toric varieties. So in these particular cases, which of course constitute an infinite amount of varieties, thanks to an algorithmic technique developed by these people, it was possible to extract the quiver and superpotential of the theory living on the D3 brane that probes these Calabi-Yau varieties. Now, what we want to do is to tackle the non-toric cases. So we want to provide an algorithm, so an algorithm technique to assign a quiver and a superpotential that would describe the resolution of the most general class of non-toric Calabi-Yau varieties. So now I intend to start to explain the framework in which we work. So instead of working in type 2E with D3 branes, we need to so our technique is based in type 2A string theory, initially compactified on trivially fibered AD surfaces. And the necessity of this approach will be probably clear later, but let me just start by giving the background. So we in type 2A string theory compactified on trivially fibered AD. So basically the six-dimensional theory engineered the singularity contains a complex scalar field that we call phi, which transforms in the adjoint of the Lie algebra associated to the singularity. And the profile of this field, so its expectation values, specify or encode the complex deformations of the surface. So if so since we want to implement Calabi-Yau geometries that are non-trivially fibered AD, we do it by assigning a coordinate-dependent VEV to this field, which automatically generates a fibration over the space parameterized by the coordinate of this, in terms of which this function is expressed. And this, so in particular, the case of the conifold that we considered before can be obtained recovered in this framework by turning on a profile for the phi field which is precisely of this form. So it depends holomorphically on the coordinate that parameterizes the transverse complex plane, and it is proportional to the Cartan element of the A1 algebra. So it can be shown that the effect of turning on this profile is obtaining a geometry that is expressed precisely by this equation here at the bottom, where you see that you recover exactly the conifold geometry. So in general, it is possible, as shown by in a work in several works by Colinucci, Valandro, and their students De Marco and San Giovanni, to a given profile for this field, which holomorphically depends on some coordinate along transverse directions. Corresponds a non-trivial AD fibration, and crucially, there is also the resolution pattern of the resulting geometry is specified by the structure, the matricial structure of this field. So what we do is to exploit this construction to focus on the implementation of the so-called simple threefold flops. So these are Calabi-Yau threefolds that exhibit only a small admit only a small resolution. So the resolution will consist in the blow up of a single P1 cycle, and they exhibit and this P1 cycle can be chosen with two different orientations. So it has precisely the same plot transition that the conifold has. So in this case, in this sense, we can interpret this special type of Calabi-Yau threefolds as non-toric generalizations of the conifold. So our present aim is to recover the threefold geometry from the moduli space of D2 probe. So to extract the quiver and superpotential of the threefold from a D2 probe instead than using the D3. So let me, in order to be as clear as possible, let me just start by considering the conifold example. So I will start by the configuration of the D2 brane that probes the trivially fibered A1 singularity. So as for the parent for the theory, we have now 8 supercharges. So the theory in 3D will be n equal to 4 supersymmetric. It has the same quiver of the 4D parent, and the superpotential couples that you see here couples the chirals phi1 and phi2 associated to the U1 vector multiplets with the hypermultiplets Q1, Q1 tilde, Q2, Q2 tilde that connect the two nodes. So in order to transition from operate a transition from this configuration to the conifold, we have to add a deformation to the superpotential, which in this simple case consists just in a sum of masses for the Coulomb branch chirals. So this has the effect upon integrating out these fields of setting to 0 the difference between these chirals and of re-expressing the diagonal or binding the diagonal combination of these two fields to a combination of hypermultiplet bilinears. And the superpotential in the effective theory will be vanishing as in the 4D case. So as a result, if one computes the invariant contractions of the hypermultiplet fields, one can obtain all the invariants that parameterize the moduli space. And in this case, one sees that the four variables satisfy trivially this relation UV equal to PQ. And upon a very simple change of variables, you can see that that relation becomes the conifold equation. And here I wanted to stress that what in the field theory basically corresponds to the motion, the center of mass, what in the field theory corresponds to the parametrization of the motion of the center of mass of the two fractional D2 branes along the base of the fibration is precisely the diagonal combination of these two Coulomb branch chirals. Whereas the fact that the difference between the fact that the difference between the two chirals is set to 0 implies that or lifted in the moduli space implies that the two fractional D2 branes now cannot move one from with respect to the other, so they must move together, and their bound state indeed forms the pure D2 brane state, which is free to move everywhere. So now I want to rewrite the deformation that I've written before in a way which is open to be like more open to generalizations. So I will rewrite this as a trace of a product of two matrices. So the first matrix is precisely the profile of the phi field that implements the conifold geometry. Now expressed in terms of the kind of a combination of fields that describes the motion of the pure D2 state along the base of the fibration. And the other matrix, mu, is an A1 moment map, which in a 3D theory, corresponds to the Coulomb branch data of the theory. So on the diagonal, you see the masses of the hypermultiplets expressed in terms of combinations of the Coulomb branch chirals. And on the off-diagonal terms, you can see the operators W plus and W minus, which are called monopole operators. And these are operators that contribute to the parametrization of the moduli space of specifically of 3D theories because they are disorder operators that are local in 3D, but basically uplift to Toft lines in 4 dimensions. So these operators will be crucial for our construction. So let me now come to the first relevant example, which is also the simplest type of non-trivial AD fibration of non-toric type. And this is called the Reed pagoda, and it can be obtained or described as a non-trivial fibration of deformed A3 singularities specified by this first equation over a complex plane, again parameterized by W. And the profile of the field of the phi field that induces the transition to this kind of geometry is the one I've written here in red. And as you can see, as opposed to the conifold case, now the coefficients of this matrix are proportional to simple elements of the A3 algebra, in particular to two of the 3 simple roots of A3. And this has very important consequences in the structure of the resolution map of the resulting geometry. Because here, by naively looking at the equation of this geometry, you would think that basically for every value of W different from 0, you have the totally desingularized A3 surface, but whenever W, so when W is equal to 0, you recover the full A3 singularity. Now, this is not actually the case in the sense that I mean, the fiber is the singularity tree, but if you try to resolve to resolve the reed pagoda, so the resolve the singular to uplift the reed pagoda to its resolved version, then you will see that in the configuration of exceptional two cycles that are blown up only consists of a single P1, which is the one that corresponds to the central root in the Dinkin diagram. And here I have highlighted in red the two leftmost and rightmost nodes, which indeed correspond to the roots along which the phi profile is defined. So what I want to do now is to show you that I can recover the quiver and the superpotential that corresponds to a D2 that probes the reed pagoda by starting from the as in the conifold case, by starting from the theory of a D2 that probes the trivially fibered A3 singularity, which in this case is represented by a quiver with the shape of a finite tree and n equal 4 and the usual n equal 4 superpotential. And now by turning on a deformation of this kind, we can operate a transition to the theory that we expected to recreate. So let me just briefly describe the structure of the deformation. So you see here that you have monopole as opposed to the conifold case. In the deformation, you don't have just trivially mass terms for the for the chiral fields in the vector multiplets, but you have monopole deformations. So and the monopoles that appear are basically the ones that are associated, so in one-to-one correspondence with the leftmost and the rightmost nodes, which are exactly the nodes that are affected by this non-trivial fibration. So in the sense that they will be the P1, the P1s they're associated with will not be part anymore of the resolution of the resulting space. So now, since even if these are local operators, they are also it's impossible to express them in as polynomials in the elementary fields of the theory. We actually require a specific technique to treat them and to trace their effect. And this technique is, is present in the literature thanks to the work of these people. And it is based on what is called the local 3D mirror symmetry. So here, as you can see, you can exploit the fact that the deformation involves only the data, so the Coulomb branch data of the two red nodes. So you can think of engaging the two central nodes and thus obtaining two subquivers, so two distinct theories, which can be glued together by gauging these nodes. And you can apply mirror symmetry locally and integrate out the fields that will become massive due to this deformation, and then apply mirror symmetry again to obtain some new effective description of the resulting theory, and glue everything back again so that in the end what you will obtain will be a quiver of this form, the one I've written here, with this effective superpotential. Where here, like you can see that you have basically this is an n equal to 2 supersymmetric theory. So these yi and zi F1 and F2 are all independent chiral superfields. And here in the superpotential, you see appearing A1 and A2, but these correspond to essentially to linear combinations of these of the loops that appear in the quiver. So this will be clear later. I will make this explicit. So now let me just tell you that so there is a clear relationship. So we can trace back the origin of these effective fields, comparing comparing them to the original theory. And you can see that basically the yi's are related to the contraction of various arrows, so of two arrows, basically. For example, y1 is related to the contraction of Q2 tilde, Q1 tilde, which are in this case Q1 tilde is the arrow connecting phi 1 node 1 with node 2. Q2 tilde is the arrow connecting node 2 with node 3. So basically, the contraction of these two arrows gives you y1, and similarly, this works with the other y's and z's. For what concerns instead the AI, instead they are related to, in a less trivial way, to linear combinations of the contractions of Q and Q tilde that basically start and end on the same node, so which give rise to eventually to loops. Okay, so now, okay, so here is the superpotential that we have. So in order to work out like the equations that define the moduli space of this theory, you have to consider all the gauge invariant operators, which I've written here, and compute the differential of the superpotential, which gives you the so-called F terms, so a series of relations between the gauge covariant coordinates, which can be re-expressed in terms of relations between the gauge invariant ones, so that in the end you see that out of six, so you have six coordinates, six complex variables parameterizing the moduli space, and eventually three relations between them. One is the one identifying A1 with A2. Another one is the trivial one, basically. And then you have an extra one relating the contractions between Y and Z with A. So you can combine these relations, which together imply a fourth relation, which is precisely the equation of the Reed pagoda. And here I have expressed, I have decided to re-express basically Y1, the contractions Y1, Z1 and Y2, Z2 in terms of the fields phi 1 and phi 3, which when integrated out are related to Y1 and Y1, Z1 and the product of A1, A2. And due to these relations, they are basically identified. And I wanted to do this in order to stress the fact that in this, so that eventually in the moduli space, the relative motion between the remaining fractional D2 branes that you would have is lifted. So you basically have no way of moving the fractional branes. So because in the total space geometry, the singular locus is just represented by a point. Okay, and this is just to prove you that basically A1 and A2 correspond to specific linear combinations of the two loops that I've written, that I've defined as F1 and F2. And upon this, I mean, interestingly, upon the replacement of A1 and A2 inside the expression of our superpotential in terms of F1 and F2, we obtain a superpotential that is perfectly single trace, as one would expect from the construction of the non-commutative algebra associated to the quiver. So as an extra, so we have applied this technique also to less trivial cases, and a very relevant one is represented by the Brown-Wilms threefold, which is an example of simple flop of length 2, and which can be realized as a non-trivial fibration of a D4 singularity over C, defined by this equation in C4. And here again, in order to obtain the quiver and superpotential of this theory, we have to turn on a deformation that involves the Coulomb branch data of the single 3 non-exceptional nodes of the quiver. So the result will be an effective n equal to 2 theory with this quiver. And the superpotential whose F terms will give rise to relations. And these relations are precisely those that, combined to the algebra specified by the quiver, describe the resolution of the Brown-Wilms threefold singularity. So to conclude and wrap up what I said, so what we essentially claim is that the quantum field theory on any geometry, of a D2 brane probing any geometry of type X3 of phi, where X3 is this non-trivial fibration of AD singularities over a plane, or essentially any kind of vibration that is implemented by turning on the phi profile, can be obtained by appropriately deforming the theory on the trivially fibered AD singularity. Then we provide a recipe that is quite simple, at least conceptually, to extract the three-dimensional n equal to 2 superpotential of a large class of non-toric Calabi-Yau threefolds. And in doing this, we complement a totally new approach. With a totally new approach, the results available in the literature and developed by Witten and Klebanov, and in particular by Cacciazzo, Vaffa, Katz, and parallelly by Gubser, Nekrasov, and Shatasvili, who also focused on monodromic fibrations of AD singularities. And lastly, we propose a physical explanation. So we describe as a physical phenomenon the operations that constitute like a non-commutative geometry algorithm implemented by the mathematician Joseph Karmasin to extract the quiver and the relations of the threefold, starting from the affine linking diagram of the associated ADL algebra. And in the future, we have the idea of generalizing our cases by studying and testing our technique by considering stacks of ND2 branes, and so proving that basically what we reproduce is a symmetric product of the probed spaces. And we aim at also generating, so reproducing the quiver and superpotential of the exceptional of fibrations of exceptional singularities, which is, I mean, technically more challenging, and then to generalize even more. So so with this, I can stop and thank you, and then I'm open to answer any questions that you want to ask.
All right, let's thank Marina. Do we have questions? So I have quite a vague one out of the like out of all Calabi-Yau threefolds that you could study, how, like, of course, the toric ones are well understood, and then you have all of the non-toric stuff. And how large of a chunk can you cover with these methods? Like,
Well,
I know that this is not a great question, like, just to get a feeling.
I mean, for sure, I mean, you can for sure you can obtain you can construct both threefolds and fourfolds, because you can construct these geometries by constructing so specifying a profile for this phi field that depends not on one complex coordinate but on two complex coordinates. So you can do various kind of implement various kind of fibrations, and you can create a large variety of geometries, but still, like, they will be rooted in the fact that they are fibrations of AD singularities, or like their origin will be given by the AD singularity structure. So I don't know. I mean, for sure, a very large class of geometries. You can construct also flops that are non-simple by composing simple flops. So it's I would say that it's a fairly large class of geometries. It's not like restricted to simple flops. This is just a first step.
Okay, thank you.
Welcome.
Do we have more questions?
So I have a question. What happens if you put multiple D3 branes?
Well, if you put multiple D2 branes, I mean, what I would expect is to have to find a symmetric product of so that the moduli space reproduces a symmetric product of real pagodas, or of the geometry that you are probing. But this is something that we still have to check. So I expect to find like the non-commutative generalization of the quivers that I found so far. Yes. So as in
before doing the deformation, you just have to take UN quivers instead of U1 quivers.
Yes.
Right?
Yes.
The question is about the quivers after the deformation.
Yes, I would expect to find quivers that have the same shape as the one, for example, as the one that I found for the reed pagoda, but the nodes, like the remaining nodes, will have the original number of branes that I put there. This is like my prediction.
More questions? Okay, then I would say let's thank Marina one more time.
Okay.
And we can go off the record.